Thanks. Hi, it is my pleasure to present our paper. My name is Lighter and Safer Than Air Containers. Hopefully, not all of you great containers, so you won't be too offended. So my co-authors are Filipe Marco, Florian Schmidt, Simon Günther, Iricia Sukata, Sudip Sati, and Felipe Guinci from NEC Research in Heidelberg, and my student Profil from the Polytechnic. Isolating workloads is still one of the main goals in clouds, where you have multiple tenants fighting for the same hardware. But even in private data centers, where workloads belong to the same organization, have to share the same hardware. So the way you get isolation traditionally is through virtualization. So we all know you have a hypervisor and then VMs that run full operating systems on top of the hypervisor. And this is great because it gives you very strong isolation that's supporting hardware for CPU protection, rings, and memory protection. However, it's heavyweight because you have to duplicate the OS kernel, all the libraries and applications and so forth, to the point where it actually takes a lot of time to boot a new VM and you can't really run that many VMs in a single box. More recently, there's been a huge shift towards containers, which are basically glorified processes, processes with added namespaces on top of them to keep better isolation. Now, the nice thing about containers is that they can share the kernel of the operating system, in this particular case Linux, and even the libraries and other services the OS may offer. And this gives you a fairly lightweight solution to virtualization. You can run many containers on a single box. However, the isolation you get is not as good as virtual machines. And to understand why fundamentally this is a problem, we have to understand that the API that the kernel gives to the container is essentially the system call API. And if you look at Linux, and we just trace the number of syscalls Linux offers versus the year, you see that there's this constant increase in the number of syscalls that Linux offers, from 200 around 15 years ago to 400 today. Now, if you want to get isolation for containers, for every single namespace you create, you have to make sure that all of these 400 syscalls implement correctly the namespace separation you're trying to provide. And that's actually quite difficult. And that's why we're seeing a lot of exploits targeting containers. So a user today is stuck between a rock and a hard place. So it's a case of pick your poison. Either you go for heavyweight VMs, or you go for lightweight containers but with poor isolation, right? So what we want to do in this work is to try and have a look at this statement that VMs must be heavyweight, and actually we set out to dispel the myth that VMs must be heavyweight. And we'll present LightVM, which is a system that gives you VMs that are as fast and efficient as containers. In particular, LightVM can instantiate, kill, or migrate VMs in tens of milliseconds or less. It has low per VM memory footprint, in the order of tens of megabytes, which means you can run from 1,000 to 8,000 or more on the same machine. Okay, so the first step in achieving lightweight virtualization is to have smaller VMs. So let's have a look at how we can get this. So typically a VM is some OS kernel, for instance Linux, with some libraries, third-party applications, and services, on top of which the user will install one or a small number of apps it really wants to run. Typically, one VM will run one interesting app. So if you actually look, you can figure out that if you take a standard Linux distro and you take the application you want to run, this application will only rely on a small subset of the software you have installed in that distro. Okay? So now the task is to somehow take only the useful parts and create a VM with them, rather than have the full standard distro that is 1 gigabyte in size or more. So we looked at two approaches of doing this. The first approach is, has been explored by many groups, and it involves unikernels. So with unikernels, you basically don't care about the OS at all. You don't care that Nginx was meant to run on Linux, for instance. You take Nginx and you compile it against a minimalistic operating system that is designed to run in a virtualized environment, such as MiniOS, or as it comes with Zen. So you compile it against MiniOS, and you also keep adding libraries until the application actually works. So you might add TLS support, you need to add a networking stack, and so forth. And at some point, you add enough functionality that the application works. What you get is a very small VM that is, that simple that it doesn't even have a user space, kernel space separation. In many cases, it doesn't even have support for processes and so forth. So this is a very simple application. But the good thing is that this is very lightweight, and it has been shown in many cases that it can provide very good performance. So we built a few unikernels for this work. The simplest one is this one we call Daytime. This is basically MiniOS compiled with a TCP server and something that responds to state. So the TCP server, if you connect to it, it responds with the current data time, right? That's why it's called data. We also build more complexity kernels. For instance, we have a Python interpreter, and we have a proper proxy determinate TLS that, for instance, CPNs might come to deploy if you terminate TLS close to the customer. So all of these are very, very small. So their image sizes are 1 megabyte, a few megabytes or less, and they need just a few megabytes of RAM to run. So this is great. Like if everyone could engineer such small VMs, you could easily see virtualization be as efficient as containers. Unfortunately, the engineering effort to create unique kernels is actually quite staggering, and it takes a lot of extra time to get the application to work in such a constrained environment. Right? You don't even have libc, so you have to sort of replace it in something else. So bearing this in mind, we also took another approach. We said, okay, can we take a standard Linux distribution and somehow make it smaller? So we created a set of tools that we call Timex. And what Timex does really, it starts from a target application and a target distro. And first it figures out what the dependencies are for this for the target application. We use ObjectDump and the DBKG, the Debian packet manager, for this. And once we figure this out, what the dependencies are, then we start with the dbootstrap file system, Debian sort of minimalistic distribution, and we use overlayfs to install the target app and dependencies on top of this initial file system. Once we do this, we basically remove the stuff we don't need, for instance, DBKG, right? And then when we unmount overlayfs, we are left with a minimalistic file system, right? And we just put BusyBox in it and we're done. So this is the distro. And then we do the same thing for the kernel, so we basically remove things we know are not going to be needed in a virtualization environment, for instance, bare metal drivers, or lots of options that are not really that useful, and we also allow the user to give us a list of options to try. We recompile the kernel automatically, boot it, and see if the application still works. So what this gives you is a very small virtual machine. So for instance, we can bring down the kernel from 8 megabytes to around 1.5 megabytes. The image sizes can be brought down from 1 gigabyte to tens of megabytes, and the resulting VM can boot in as little as 200 milliseconds compared to 2 seconds for a standard Debian distribution. So this is actually not bad. Now the question is this enough? So to see whether this is enough, we basically started and tested multiple ways in which you can isolate workloads. So the first one is the process, right? That's the basic isolation. We just basically ran sleep and sleep and from bash, and we measured how long that takes. And on the x-axis, I have the number of running processes or guests, and on the y-axis, I have the time it takes to boot another one, right? So basically, if you see, if you boot the process, it takes around 1 millisecond or something like this. Now the green line shows what Docker takes to boot the new container, right? So booting the new container in Docker takes around 200 milliseconds. Roughly. And it doesn't really matter how many Docker containers you have running, it takes roughly the same amount of time. Now, if we boot a Debian virtual machine, I have these two lines. So the bottom line is the time it takes to create the virtual machine, and the top line is the time it takes until the virtual machine actually boots. Okay? So to the left, we have 500 milliseconds to create the virtual machine, and 2.5 to boot. And to the right, it's actually quite bad. So it takes 82 seconds to boot the virtual machine number 1000. Okay, so this is actually quite bad. But it's not just Debian that suffers. So if we put our very small daytime VM, the unique kernel I mentioned earlier, this is what the numbers look like. So they start well, it's more efficient than Docker on the left. But then as you have more and more VMs running, it becomes less efficient. And the same thing happens for Timex. Okay? So there's something going on here in Zen, which is our virtualization system that we targeted, and we need to understand what it is. So before I can tell you what the problem is, let me quickly run you through what Zen does. So Zen runs this special VM that's called Domain 0 that is in charge of managing the machine. Okay? So Domain 0 also runs the bare metal drivers, for instance, the network interface driver. Okay? And for every VM, it has a virtual driver that talks to the VM and gives the VM, for instance, networking access or disk access. So the tool to create VMs is called XL, and it comes with a tool stack, a bunch of libraries that basically enable VM creation and deletion and so forth. And finally, there are some software components that are used to make the virtualization system work, including the software switch and a component called the ZenStorm. The ZenStorm is actually quite important. It's like a proc file system, if you want, but it can be accessed by all the virtual machines, and it is used to store configuration data and to basically synchronize virtual machines when they're boot. Okay, so now if you want to create a virtual machine, the XL will basically create the shell, create some virtual drivers, and then the VM is good to go. So we went and did a breakdown of where the time is spent in Zen when you create a virtual machine, and this is what it looks like. So the x-axis, again, I have the number of already running guests, and on the y-axis, I have the time it takes to run, now broken down by the different components. And what we see is that we have two main things that are contributing to this overhead. One of them is XenStore, and the other one is creating virtual devices. So to understand why the XenStore is such a big problem and why it adds to this humongous increase in creation time, let's just look at what it does and how it is used. So I'm showing here the three main components that are interacting when the VM is created. I'm just focusing on the part where it creates a single virtual device. Okay, so the VM has been created, memory has been allocated, now we're just creating one virtual device. Okay, so the tool stack will run to the right to the XenStore in a transaction a bunch of entries. The backend, which is running typically on the same operating systems, will get a notification from the XenStore, and it starts creating the virtual driver, the virtual device driver, and after it creates the virtual device driver, some user space process writes to XenStore. At this point, there's another notification, some other entries get written to XenStore, at which point the front end gets activated, and then we have this negotiation starting between the backend and the front end to decide, are we using segmentation offload and so forth. So basically, there's this back and forth all the time, and at the end of the day, you have a lot of XenStore entries written in red for every single device driver, more than 30 entries. Every single one of these interactions require crossing privilege domains, so you go from user space to kernel space to hypervisor and back multiple times. And this really makes the XenStore a big contention point for the whole system, and this slows it down. And this inherent inefficiency is coupled with some implementation problems that XenStore has. For instance, it checks some for UDP by using linear search. So that's not really fixed, but there's more fundamental. Okay, so LightVM is our solution to the problems that Xen has. And at the high level, this is what we do. We basically take Excel, which is the tool stack that Xen provides, and we replace it with Chaos, which is our own tool stack. Chaos, there's nothing really special about Chaos except that it's written from scratch to be fast and supports para-virtualized guests. So, as I said, there's not many big principles in it. It's just much faster, as I'll show you in the experiment. Now, we also observed that if you split the VM creation time in two phases, it can actually go much faster. And the final part, which is a big architectural change to Xen, is to remove this XenStore and to replace it with something that's distributed. So let's look into details a little bit. So first, let's see what you do when you create a VM. So you first talk to the hypervisor and you reserve the VM, then you basically allocate a virtual CPU, then you allocate some memory, then you create some device driver stubs. And at this point, you can parse the configuration, actually initialize the devices, build the image, and boot the VM. Okay? Now, we observe that these 5 steps are more or less independent of the VM, right? It doesn't really matter what VM you're starting, these steps will be the same for all VMs you're starting. So what we do is we basically split the tool stacks in two parts, One part that is a daemon and runs basically all the time, and this one creates empty shells of VMs. Right, and the empty shells will have different sizes to allow for variability in the image size of the VM. And then when someone actually wants to create a VM, we take an empty shell, and we basically run just the last 4 steps. And intuitively, this should be much faster. Okay, the next step I would like to tell you about is how we replace the XenStore. So the XenStore at the high level is used for 2 things: to store data, for 2 things: store data, communicate between guests, and synchronize guests. Replaces these 2 parts with shared memory. So we allocate some shared memory pages between the front page, the DOM0 basically, and every guest VM, and we synchronize them using these Xen software interrupts that are called event. So how does this work? Again, I will walk you through the process of creating a virtual device. So the tool stack now talks to the backend through an IOCTL, so this is just a Linux syscall. The backend will create a shared memory that it uses to communicate with the front end, with the virtual machine. And then it tells the tool stack what the address of this memory page is, and it gives it the right to basically map. Okay? This information is written into a device info page that the front end has access to. So the front end, when it starts, it maps this device info page automatically in its own memory space. So there's a notification coming, basically a Xen event, and at this point, the front end knows it has to read the device info page. It figures out that, although we're initializing a new device, so we can map this page and directly read and write from this page without any overhead. So the shared memory basically cuts all domain crossings and overheads for reading and writing data, and then we basically use event channels for amplification. And this is basically turns the XenStore, which is a centralized piece of a centralized component into something that's completely distributed. Okay, so how well does this work? The basic experiment is the same, right? So we want to instantiate some number of VMs and containers and see how long does it take to instantiate the end VM or thing. And the bottom line here is like VM, booting a unikernel, putting the data in unikernel. So this is a very small unikernel, as you may know, so this is sort of a lower bound in what we can do. Okay, so it basically takes 4 milliseconds, regardless of how many VMs you have running, which is what you want and would expect. Note that it takes around 1 millisecond to start do a 4 gigs on Linux, so this is actually not bad. The nice thing is that Timex, which is a full Linux distro running over LikeVM, gives comparable performance to Docker containers, especially when you have less than 800 of them running. From 800 onwards, every Timex VM will do some small amount of processing, and that basically increases the load on the machine, and that's why you get that small increase at the end. Okay, and if you, so this is actually quite nice. Now, let's look at how many we can instantiate. So, if you try and put as many Docker instances on our machine, you can go up to 3,000. This is a 128 gigabyte machine. At that point, we run out of memory. Okay? With LikeVM and unikernels, we can basically go to up to 8,000 and with very stable instantiation. So this is all great, but where are the benefits coming from? So this is the initial line. This is the Excel tool stack without any of our changes. And if you just replace Excel with Chaos, which is our rewrite of Excel, you get a 4 to 16x improvement in performance just because Excel was not really optimized for speed. Right? When you have VMs that are a few gigabytes, it doesn't really matter if it takes 5 milliseconds or 30 minutes. Right? Whereas for our LikeVMs, it does. Next, if we enable the split tool stack, what we managed to do is to get rid of some of this linear increase when you add more and more VMs, and this is because the XenStore interactions are basically done ahead of time. Okay, the pre-creation case. Next, if you also use Chaos with the no-XenStore approach, you get around 5 to 8 millisecond boot times, and finally, if you enable all optimizations, you get that line software. Okay, so this is all great, but what can you use it for? So I will tell you a little bit about some use cases we have thought about. There's more in the paper, so please have a look at that. One interesting use case is for mobile operators. So this is the mobile network. There's a bunch of cells connected to the core network connected to the internet, and then you can connect to any cell number of mobile devices, the thousands. Now, what mobile edge computing, which is a new trend, mobile edge computing says, let's deploy some processing close to these cells, a small number of servers, one or a few, and then we can offload some functionality from the mobile to these servers. Of course, how do you offload? Ideally, every VM should have its own functionality in there, right? So every mobile, you have to have like a few thousand of them running. But if you use normal virtual machines, you can't do it. If you use containers, you get more isolation. So this is what we did with LikeVM. So the first thing we looked at is having one firewall per client. And the firewall we instantiated with a ClickOS unikernel. And basically what we measured here is the number of VMs we have running, so the number of customers that are actively sending. Each of them is sending 10 megabytes of traffic, and I'm measuring the aggregate throughput that our box can forward from all these virtual machines. And in aggregate, we can do around 3.9 gigabits. And the nice thing is that one cell is limited to 3.3 gigabits. This is the theoretical maximum bandwidth for LTE, which means that if you put one of these servers close to a cell, we guarantee that processing using VMs won't be a bottleneck even if you have one VM per user. Another way to do this is to say, well, I'm not going to put any VM, I'm just going to put the VM whenever the client wants some service. And here we just measure a very simple thing. So the client pings our box, and the box boots a VM, the VM replies to the ping, and then that's it, right? And this is the CDF of the ping times measured by the client. And again, this is actually very, very good because 90% of the clients will see 20 milliseconds or less RTT in a fairly high load scenario. Okay, so a little bit about related work. Interclear containers are the closest one to ours. Their target is to basically run containers in VMs to give better isolation. But because of this stacking of virtualization solutions, the performance is actually a bit worse than what we can do. And also the guest stages are more inefficient. And a bunch of other works I looked at unikernels and getting them to work fast, but basically that work only looked at very small numbers of active VMs, and they only focus on unikernels and not Linux VMs. Alright, so to wrap up, LikeVM gives you lightweight virtual machines. It's possible to have both strong isolation and be lightweight at the same time. And we achieve this through lightweight guests and a architected tool stack. And I wonder if I have time to do a very quick demo now. It just takes 1 minute. Alright, so what I have here is two machines. On the left, I will do the regular Zen tool stack. So I have a list here. This shows me that I have a single running domain. And then what I'll do now is basically start 1,000 daytime virtual machines. And let me just see. So what I want to do now is Excel this, right? Okay, so as you can see, the number of VMs is increasing. Here on the right, I will use LikeVM to do the same thing. So the first thing I want to do is to create a bunch of shells for my VMs. So -m tells me how much memory it is. Okay, and I'm creating 1,000 shells. Okay, so that should be done. Again, if I do here, well, if I do chaos now, I will see the empty shells, but they haven't moved yet. So now, if I do the same thing, basically I will run 1,000 VMs using this. I'm just thinking now. Right. So this should take a few seconds, and then yeah. Okay, so it took around 11 seconds. So let's just ping the last VM that was booted. 6.9.233. Okay, so this replies, and in the meantime, Zen is still putting like the 400th version. Thanks.
So we have a number of questions from the internet. So Zhen Wan asks, basically, how do you think that these techniques might work if you apply them to containers, right? So if you took a container-based system and also stripped it down, would there be similar improvements?
Absolutely, I think it's actually slightly easier for containers, right? The fact that you can reuse parts of your kernel and libraries for containers, it should be, yeah, it should be no problem getting that type of performance. So definitely, if you re-engineer Docker to do fast boot times, there's no fundamental problem with getting similar boot times. It's just that they haven't done it and you haven't done it. I mean, we don't need to show that we basically kick their ass. We just need to show that it's fast enough that it's comparable to processes and you can't go much faster. That's basically the thing. Of course, you can get Docker to move it fast, but I don't think that's been their goal yet. Yeah.
Hi, I'm from Huawei. So I'm not sure if I understand. Did you ever mention how much management effort to get holistic OS in one specific?
So creating a unikernel is quite a bit of effort. So we're talking, I don't know, maybe a person month of someone actually knows what they're doing for the TLS termination proxy, something like that.
So it's not automatic.
Sorry?
It's not automatic.
No, absolutely not. So unikernels are definitely automatic and they are very, very difficult to create. So actually we acknowledge that, and I think Pinix, which is this set of tools to help you create a smaller Linux distro is the right way to go. I mean, this is our first cut at it. I mean, it's reasonable, but I think there's much more to be done in that space, and we're looking into how you optimize and make it as easy as creating containers.
Nathan Dalton from UPenn. Really cool work. I'm interested, you went from message passing and then synchronization to shared memory. And you probably thought about this, but I'm just wondering, what's the impact or the implication on security? Side channels, linkages, because now you're sharing pages in different ways.
So the thing is, we basically just took exactly the same protocol, device initiation protocol that was used before, and more or less the same permissions that guests had in the Zen store, and we mapped them into the shared memory page. So it's not like that the guest can read more or can write more than it could do before. So I don't think there's a big issue there, to be honest. But I mean, we haven't really looked into that carefully. So the protocol, the initialization protocol is exactly the same. We haven't changed anything. It's just that instead of going to the Zen store, it just goes directly via these the shared memory plus event channels.
So Anonymous asks, what if you run multi-process applications like Apache since scheduling is removed from VM? That's an example.
Well, yeah, that's obviously a good question. So, I mean, to be honest, scheduling in VMs is a long-standing problem. So it's not like we're targeting. You can use any existing solutions, right, to optimize it. It's not. Yeah, I think that's sort of a problem, right?
All right, thanks. You go one more time.